Chapter 6, Inner Product Spaces, Section 6.1, Inner Products. An inner product on a real vector space V is a function that associates a real number uv with each pair of vectors in V in such a way that the following axioms are satisfied for all vectors uv and w in V. So we need that uv is the same as vu. We need that u plus vw is equal to uw plus vw. So it splits cross addition. We need that k times uv is k times uv, so the k factors out. We need that any vector with an inner product of with itself is greater than or equal to 0, and a vector taken with itself as the inner product is equal to 0 if and only if that vector was the 0 vector. So if we have those four axioms, then we have an inner product. A real vector space with an inner product is called a real inner product space. So if you have a vector space and it also supports these four axioms, then it's an inner product space. The inner product uv equal to the dot product u dot v, which remember is defined by just multiplying each of the corresponding components and adding them up, of two vectors in u and v and Rn is called the Euclidean inner product. So in other words, the dot product we already did is a special example of a one type of inner product called the Euclidean inner product. So that means we're going to be looking at other inner products. So you could think of it as alternatives to the dot product. This is also called the standard inner product on Rn. To distinguish it from other possible inner products that might be defined in Rn, we call Rn with the Euclidean inner product Euclidean n space. If V is a real inner product space, then the norm or length of a vector in V is denoted by norm of V, and it is defined by the square root of the inner product of the vector with itself. The distance between two vectors is denoted by duv, and it is defined by the norm of the difference between the two vectors. So what we're basically saying is take the inner product of u minus v with u minus v, take the square root of that, and that's the distance between two vectors. A vector of norm 1 is called a unit vector. So next up, if u and v are vectors in a real inner product space V, and if k is a scalar, then the length of v is greater than or equal to 0 when it equals 0 if and only if v is the 0 vector. We can pull out the scalar. Basically, these follow from the properties of the inner product. Since you can pull out scalars from inner products, you can pull out the scalar from the length. The distance between u and v has to be equal to the distance between v and u. That should make sense from the definition, since the inner product of a scaled vector is the same as pulling out the scalar. So that means that if I look at u minus v, then that would be the same as looking at minus v minus u. In other words, if I were to switch this and do v minus u, then that would be the square root of v minus u. Forgot v minus u. But then I could just pull out the minus over here, right? Because this is the same thing as minus times u minus v. So I'd pull out the minus from this one, I'd pull out the minus from this one, the two minuses would cancel, give me a plus. The way I could pull out the minus from this one is I could just change the order, because remember, the inner product of u and v is the same thing as the inner product with v and u. So the two minuses cancel, give us a plus, so this thing would end up being equal to this thing. You might want to spend some more time to convince yourself that's true, but in any case it is, and duv is greater than or equal to 0 with equality if and only if u is equal to v. If we have w1 through wn, positive real numbers, which we will call weights, and if u equals u1 through un and v equals v1 through vn are vectors in Rn, then it can be shown that the formula uv is equal to w1 times the first u1, v1, first components of u and v. So this is a small typo. There's not supposed to be a comma there because it's being multiplied. And then w2 multiplies by u2, v2, and so on. wn multiplies through un, vn. So that defines an inner product in Rn that we call the weighted Euclidean inner product with weights w1 through wn. So how about we do an example where we verify that the weighted Euclidean inner product actually does satisfy the 4 inner product axioms. So we'll check each axiom kind of like the way that we checked before for things being vector spaces and whatnot. So the first one states that uv should be vu, so let's look at what the inner product with u and v is. So that's 3 times u1 v1 plus 2 times u2 v2, because that's what they told us the inner product should be in this example. So it's just basically a dot product, u1 v1, u2 v2, but it has some weights, and the weights don't have to be the same. So in this case, w1 is 3 and w2 is 2. Well, this is the same thing as if I changed the order, right, of these two guys. So I could rewrite this as 3 times v1 times u1 plus 2 times v2 u2. And notice that is just the inner product with v with u. Oops, v with u. Great, so it is symmetric. Let's see if we can spread it out over addition, separate addition out. So let's let w be the vector w1, w2. And let's look at what u plus v inner product with w should be. So that's 3 times the first component, which is u1 plus v1. That's the first component of u plus v. And I'll multiply that by first component of w, which is w1. Add that to 2 times u2 plus v2 times w2. So I'll multiply out the w's. So I'll get 3 times u1 w1 plus v1 w1 plus 2 times u2 w2 plus v2 w2, and that equals, when I distribute the 3 and the 2, and I'll move together the u1 and u2 terms so that it looks like I have a 3 and a 2 in each set. Here, I'll show you what I mean. I'll take 3, I'll distribute it, and I'll take the 2 and distribute it also. And I'll group together the 3u1 w1 with the 2u2 w2 so that I get an inner product that was defined above. So I'll get 3u1 w1 plus 2u2 w2, just out of this times this plus this times this, and then the remaining components will be 3v1 w1 plus 2v2 w2. And I wrote it like that because now I can very clearly see that this is an inner product as defined in the example, and this is an inner product as defined in the example. The first one is the inner product between u and w, and the second one is the inner product defined between v and w. Okay, so that's great. So then this does satisfy the second axiom because it splits over addition. Let's look at number 3. Third axiom was for the constants being able to be pulled out, so let's see if we could do that. K times u, inner product with v, well, that's equal to 3 times k u1 times v1 plus 2 times k u2 times v2. Okay, so how about I factor out k. So I'll get k times 3u1 v1 plus 2 times u2 v2. Well, that's cool because that's just k times the inner product with u and v. Okay, how about number 4? Let's look at what happens when we take the inner product of v with v. Okay, so that's 3 times v1 times v1 plus 2 times v2 times v2. So that's 3 times v1 squared plus 2 times v2 squared. And because these are both squares, they can't be negative. So this thing will definitely have to be greater than or equal to 0. Okay, so that means that we have the inner product greater than or equal to 0, but we also can see that the inner product of v with v will be equal to 0 if and only if we have v1 is equal to 0 and v2 is equal to 0. That's the only way to get that equal to 0. So v1 would have to be equal to v2, which would have to be 0. But that's the exact same thing as saying that v would have to be the 0 vector. Okay, so this inner product actually does satisfy the 4 inner product axioms, so the weighted Euclidean inner product is an inner product. How about we calculate the length of u and duv for the vectors u equals 1, 0 and v equals 0, 1 in R2 with the Euclidean inner product and with the weighted Euclidean inner product from example 1. So we'll show that we actually do get different lengths and distances depending on what inner product we're using. So it's very important to choose the right inner product for the problem, or just pay attention to what inner product is stated in the problem. So let's look at the Euclidean one first. So for the Euclidean inner product, we have that the length of u, or the magnitude of u, is equal to the square root of 1 squared plus 0 squared, because we're looking at 1, 0, and that's equal to 1. And how about the distance between u and v? Okay, so that's u minus v, and then we take the length. So that's the length of, well, we have 1, 0 minus 0, 1. So that's 1 minus 1. And the length of that is just the square root of 1 squared plus minus 1 squared. So that's square root of 2. Okay, let's check weighted Euclidean now. And this is not the general weighted Euclidean. This is specifically the one from the previous example, where we had the 3 and the 2. There could have been any constants in the more general weighted Euclidean. We just chose a specific one. So we're looking at the length of u, and that is going to be the the weighted Euclidean inner product of u with u. And I'll take the square root, same thing as raising it to the 1/2 power. I'll just write it that way for some reason. So that's 3 times 1 times 1 plus 2 times 0 times 0 to the 1/2 power, which is 3 to the 1/2 power, aka the square root of 3. Okay, how about the distance? So the distance between u and v is equal to the length of u minus v, which is let's see, the length. So take the inner product of 1 minus 1 and 1 minus 1, raise that to the half power. Right, the same 1 minus 1 we were looking at before. But this time it's different inner products, so it says that we should do 3 times 1 times 1 for the first component, plus 2 times minus 1 for the second component. Raise that to the half power, and we get the square root of 5. So much different distance, much different length depending on our inner product chosen. If V is an inner product space, then the set of points in V that satisfy the length of U equal 1 is called the unit sphere, or sometimes the unit circle in V. So as an example, how about we sketch the unit circle in an xy coordinate system in R2 using Euclidean inner product. So this is our standard Euclidean inner product. So we have, let's say, our vector u is just equal to xy. So that way we could look at it in the xy plane. Then the length of u is equal to the Euclidean inner product of u with u raised to the 1/2. So that would just be the square root of x squared plus y squared. So if we have that equal to 1, then that's the same thing. Well, I'll just write it, square root of x squared plus y squared equals 1 is equivalent to saying that x squared plus y squared is equal to 1, because it's just 1 squared if I square both sides. So hopefully you remember that is a circle, which is one of the reasons we call this the unit circle. So we have the vector u, length 1, it points to all of these points that go around in a circle. Radius is 1, length of u is 1. Okay, but how about if we use the weighted Euclidean inner product 1/9 u1 v1 plus 1/4 u2 v2? Well, then it'll look a little bit different. Let's set u equal to xy again. And let's look at the length of u this time. So remember, inner product of u with itself raised to the half. And that's the same thing as the square root of 1/9 x times x is x squared plus 1/4 y times y is y squared. So a little bit different in this case. If I set the square root of 1/9 x squared plus 1/4 y squared equal to 1, then I could square both sides and get x squared over 9 plus y squared over 4 equals 1, and our unit circle in the xy plane ends up becoming an ellipse. So now we have, that's not so good. How about try a little bit harder? Not much better, but that's okay. Here's 3, here's 2, right? And here's an arbitrary vector with length 1 under this inner product. So the unit circle doesn't have to necessarily look like a conventional circle, depending on the inner product used. The Euclidean inner product and the weighted Euclidean inner product are special cases of a general class of inner products in Rn called matrix inner products. To define this class of inner products, let U and V be vectors in Rn that are expressed in column form, and let A be an invertible n by n matrix. It can be shown that if U dot V is the Euclidean inner product on Rn, then the formula UV equals AU dot AV also defines an inner product, It is called the inner product in Rn generated by A. As an example, how about we show that the standard Euclidean and weighted Euclidean inner products are special cases of matrix inner products. So let's look at the inner product of U and V. So that would be the identity I times U dotted with the identity I dotted with V, which is U dot V, in the case that we have the inner product generated by the identity. So we're setting A equal to I in this case. So if you set A equal to I in this equation over here, you just get the dot product. So that means the dot product is a special case of the matrix inner product with the identity chosen as the matrix. Let's see if we can get the weighted Euclidean inner product now. Well, the weighted Euclidean inner product, that's W1, oops, I need a W. W1 U1 times V1 plus W2 times U2 times V2, and so on. So we should end up with Wn, Un, Vn. So that would be the inner product generated by the matrix A, where each diagonal entry is the square root of one of the W's. Right? Because then if we take this matrix and multiply through the diagonal entries, we'll end up with each successive component. So actually maybe I'll put zeros in the rest of it. So that way only the W's end up multiplying through. So we just get lots of zeros, and then I'll just keep going and placing W along the diagonals. And I'll end up with the square root of Wn. So if I took this matrix A and I multiplied it by U and I multiplied it by V and dotted them, then the W1, square root of W1 and multiplied by square root of W1 give me W1 times the first component, and so on for each successive W along the diagonals. The weighted Euclidean inner product discussed in example 1 is the inner product in R2 generated by what matrix? Well, let's write it out. We had UV equal to 3U1 V1 plus 2U2 V2. So that is generated by the matrix A equal to the square root of the W's in the diagonals, right? So the first W is 3, so I'll take square root of 3. The second W is 2. Let's take square root of 2, put those in diagonals, put zeros elsewhere, and that's how we can build our matrix A. If U equals U and V equals V are matrices in a vector space MNN, then show that the formula UV equals the trace of U transpose times V defines an inner product in MNN called the standard inner product on that space. Okay, let's set U equal to an arbitrary matrix. How about we do it 2 by 2, and we'll pretend that we did it for n by n, because it could generalize fairly easily. So I'll have U1, U2, U3, and U4 as the components as the entries of this matrix, and I'll have V equal to the matrix V1, V2, v3, v4. Let's look at the inner product of u with v. So in this case, that's the trace of u transpose v. Okay, so if we take u transpose, so that switches these guys, right? Because this first row becomes the first column, so the u moves down over here, the u2, but u1 stays over here when we do the trace, and u4 stays over here when we do the trace, so the diagonal entries don't change. Remember though that when we multiply matrices, we do it row and by column. We do the row in one matrix times the column in the other. So if we're interchanging rows and columns in one of the matrices and the diagonal numbers don't change, then the u1 will multiply by the v1, but then u3 will end up over here at u2, so it'll multiply by v3 because it'll be in the first row, so it'll multiply by the first column. So we'll have u1 times v1 plus u3 times v3 for the first entry in the product. And similarly, for the other diagonal entry that we need in order to do the trace, we'll end up with u2 times v2 plus u4 times v4. So that's kind of cool, and it makes a little more sense now why we chose this strange formula to be the standard inner product on the matrix vector space MNN. So we'll get u1 v1 plus u2 v2 plus u3 v3, I don't like that u, plus u4 v4. And we'll look at the length of u. So that would be the square root of the inner product of u with u. So that's the square root of the trace of u transpose times u. So that's the square root of u1 squared plus u2 squared plus u3 squared plus u4 squared. Okay, let's set u and v into some specific matrices just as an example. How about I take u equal to the matrix u equal to, say, 1, 2, 3, 4. Make it a little more concrete. I'll take v equal to the matrix v equal to -1, 0, 3, 2. Then if I look at the inner product, then that's just the trace of u transpose v. So that's 1 times -1 plus 2 times 0 plus 3 times 3 plus 4 times 2. So you can see that the reason why we use this formula is just to get all of the corresponding components multiplied together. If I want the length of u, then that would just be the square root of the inner product of u with u. So that's the square root of the trace of u transpose u, which is the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. So that's square root of 30. if I wanted the length of v, I could similarly get it. Square root of inner product of v with v. So that's the trace of v transpose times v, which is the square root of minus 1 squared plus 0 squared plus 3 squared plus 2 squared, which is the square root of 14. So to really correctly answer this example, we would, in order to show that the formula defines an inner product of n, we would have to go through each of the inner product axioms. I'm not going to do that because I think that given this example and given this explicit formula for the inner product, you can see that it's basically just a dot product on the components. And as we saw previously, the dot product is definitely an inner product. Oh, and also clearly it generalizes to nn, for the same reasoning as in the 2x2 case. Let's move on to this next example. If p and q are polynomials in Pn, then let's show that the following formula defines an inner product in Pn that we call the standard inner product on this base. So we take each of the coefficients and we multiply them, and then we add them up. So all of these are pretty similar to the dot product that we're used to, just we have to adjust it slightly, so that it ends up looking like a dot product in the end. By the way, look at the length. The length of a polynomial under this inner product would be equal to the square root of each of the coefficients squared. So that'd be a0 squared plus a1 squared, and so on through an squared. Okay, let's check each axiom for this example. So let's do number 1. We're looking at p, the inner product of p with q. So that's equal to a0 b0 plus a1 b1, and so on through an bn. And that's equal to the same thing if we switch it, b0 a0, because multiplication for real numbers is commutative. So b0 a0 plus b1 a1, and so on. We just swap the a's and b's, which gives us the inner product of q with p. So first axiom is good. Let's do the second. Let's set some r equal to c0 plus c1x plus, and so on through cn xn, so that we have a third polynomial to work with. And this way we can look at the addition of p and q, inner product with r. So that's a0 plus b0 times c0 plus a1 plus b1 times c1, and so on, till we get to an plus bn times cn. We'll set that, we'll distribute the c's. This is pretty similar to what we did before when we were proving this axiom. So, well, proving the axiom holds in the other case that we did. So we distribute it, we get a1 c1 plus b1 c1 all the way through an cn plus bn cn. And that'll equal a0 c0 plus a1 c1, and so on, an cn. So plus b0 c0 plus b1 c1 all the way through bn cn, and I separate it that way so that I can view it as two new inner products. We have now the inner product of p with r and the inner product of q with r. Okay, let's check third axiom now. So we're looking at some constant k times p, inner product with q. So that's k times a0 b0 plus k times a1 b1 and so on all the way through k times an bn. I'll factor out k. I'll get k times a0 b0 plus a1 b1 all the way through a and bn, which is just k times the inner product of p with q. Okay, number 4. Let's check the inner product of p with itself. So that's a0 squared plus a1 squared all the way through an squared. And all those are squares, so they have to be positive or greater than or equal to 0, not negative. Let's look at the inner product of p with itself. That has to be 0 if and only if all of those coefficients are 0. So a0 has to be 0, a1 has to be 0, and so on. Which is the same thing as saying that p would have to be 0. The entire polynomial would have to be the 0 polynomial. Next up, if p and q are polynomials in Pn, and if x0 through xn are distinct real numbers called sample points, how about we show that the formula pq equal to p evaluated at x0, q evaluated at x0, plus p evaluated at x1 times q evaluated at x1, and so on, defines an inner product on Pn called the evaluation inner product at x0 through xn. Well, first of all, 1 through 3 follow immediately from properties of the dot product, similar to the matrix example that we looked at. When you evaluate polynomials at numbers, they just become numbers. So 1 through 3 are pretty clear. There really is only one spot here we have to be careful, and that's with property number 4. Because with property number 4, we have to have the inner product equal to 0 if and only if the polynomial is 0, so we just have to verify that. So let's go through 4 carefully. First, if we take a polynomial and we look at the inner product of that polynomial in itself under this evaluation inner product, then that's just the same thing as taking the polynomial evaluated at x0 and squaring that, adding it to the polynomial evaluated at x1, squaring that, and so on, all the way through xn, and all those squares will clearly have to be greater than or equal to 0, as we've already seen. So let's look at the interesting case where we have the inner product of a polynomial to polynomial equal to 0. So that means that the polynomial evaluated at x0 has to be equal to the polynomial evaluated at x1, has to be equal all the way through to the polynomial evaluated at xn, and all of those have to be equal to 0. So if the polynomial evaluated at x0, x1, and so on through xn is 0, then that means that x0, x1 through xn are all roots of the polynomial. Notice from 1 to n, that would be n roots. With x0, that gives us n plus 1 roots. However, the polynomial is in Pn, so it's an nth degree polynomial. So by the fundamental theorem of algebra, if it's not 0, it should only have n roots. Since it has an extra root, the only way for that to be possible is if it's the 0 polynomial. So P must be equal to 0 by the fundamental theorem of algebra. Okay, so now we've shown that the evaluation product is actually an inner product. Notice that the length of a polynomial, P, under this inner product is just equal to the square root of the inner product of the polynomial with itself. So that means that it's equal to the square root of P evaluated at x0 squared plus P evaluated at x1 squared, and so on, all the way through P evaluated at xn squared. How about we let P2 have the evaluation in a product at the points x0, x1, and x2 given, and let's compute PQ and the length of P for the polynomials P and Q given. So what we'll do is we'll write out PQ. So that's equal to P evaluated at, let's see, the points are -2, 0, and 2. P is x squared. So that means what we'll do is P of -2 times Q of -2 plus P at 0 times Q at 0 plus P at 2 times Q at 2. Okay, so P at -2 is x squared at -2, so -2 squared is 4. And then Q is 1 plus x, so 1 plus -2 is 1 minus 2 is -1. Plus P at 0, 0 squared is 0. And then 1 plus 0 is just 1 for Q. And then 2 squared is 4. And 1 plus 2 is 3. Adding all that all up, we get 8. Now let's get the length of P. So we'll take the square root of P at x0 squared plus P at x1 squared plus P at x2 squared. And our first point was -2, so that's P of -2 squared plus P at 0 squared plus P at 2 squared. So we get square root of 4 squared plus 0 squared plus 4 squared. So that's the square root of 32, which is 4 radical 2. How about we let f and g be two functions that are continuous in the interval ab, so they're in CAB, and let's define that inner product as the integral of the product of the two functions. And we'll show that this formula actually does define an inner product on CAB. So let's look at each axiom. For number 1, let's look at the inner product of f and g. So that'll be equal to the integral from a to b of f of x times g of x dx. But multiplication of functions is commutative. So that's the same thing as the integral from a to b of g of x times f of x dx. So that's just the inner product of g with f. So the first axiom is done. That was easy. Let's look at the second one. Let's look at f plus g. And we'll take that inner product with another function, let's say h. So that'll be the integral from a to b of f of x plus g of x times h of x dx. And that's equal to the integral from a to b of f of x times h of x dx plus the integral from a to b of g of x times h of x dx, because all we did was distribute h and then apply the linearity property of integrals to separate out the two integrals. So that's just fh, the inner product, and added to the inner product of g with h. Okay, let's look at number 3. If we take a constant times f, we take that inner product with g. That's the same thing as the integral from a to b of k f of x g of x dx. And again, by linearity, we could pull out the constant. So that's k times the integral of f of x g of x dx, which is just k times that inner product. So that takes care of number 3. Lastly, number 4. If I look at the inner product of f with f, then that's the integral from a to b of fx times f of x, or f squared x dx, if you like that notation, which has to be greater than or equal to 0. Anything times itself, any square is going to be greater than or equal to 0, and then the integral of that would have to be greater than or equal to 0. How about the... So that means that the inner product of f with f can only be equal to 0 if and only if, because remember the integral can only be 0 if the function is 0 on the interval. So that was a, b. But that is only the case if and only if we have f equal to the 0 vector. If f is a 0 function, f is a 0 vector. If CAB has the inner product that was defined in example 10, what is the norm of the function f relative to this inner product? Well, let's see. The norm of f is equal to the inner product of f with itself raised to the half power, which is just, by definition, of the inner product that we're given, equal to the square root of the integral from a to b of f squared of x dx. Well, that's kind of cool, but that means that, even though they didn't ask, but the unit sphere, in this case, would be equal to the set of all of the functions f that are inside of CAB. So all of the functions continuous on AB, such that when you take their integral of the f of x squared dx, you get 1. So not exactly what you would expect from the unit sphere or unit circle. It's an interesting inner product. Notice this is a lot different than the length that you look at in calculus, the arc length. Because in calculus, and I'll write as an aside that this is not equal to the length from calculus, which is defined as the integral from a to b of the square root of 1 plus the derivative squared. So we have to be a little bit careful here, because in this case the vector length that we look at in relative magnitude relative to our inner product is very different than the length that we're kind of used to from calculus, which is the arc length given by the integral of the square root of 1 plus the derivative squared. This was the function squared, this was the derivative squared. If u, v, and w are vectors in a real inner product space V, and if k is a scalar, then we have all of these properties over here. And we could prove them using the definition of the inner product and the other things that we've looked at so far, but most of them are fairly straightforward. If you take the inner product of 0 with a vector, then you're going to get 0. It turns out you can distribute addition in the second component. That should make sense because you could always swap these, right? You can also distribute subtraction, and you can also distribute subtraction in the first component. So, and you can distribute the scalar to either one. So you get all of those for free. As an example, how about we compute u minus 2v, the inner product with 3u plus 4v. In terms of the lengths of u, v, and the inner product of u and v. So we'll take u minus 2v, inner product 3u plus 4v. That's equal to, well, how about we separate off the u? Get u by itself. So we'll keep the 3u plus 4v in both, and it was minus 2v, so we'll subtract off 2v inner product with 3u plus 4v. And then I can split over here in the second component, so I'll get u inner product with 3u plus u inner product with 4v. So that takes care of this. And then minus, but I split this one too. So minus 2v inner product with 3u minus 2v inner product with 4v. Okay, so I can pull out the 3 now. So that's 3 times u inner product with u plus, I can pull out this 4. Remember, it doesn't distribute to both for inner products. You only pull it out of one component. So that's 4 times inner product with u and v minus 6 inner product with v and u, because I pull out the 2 and then I pull out the 3. 2 times 3 gives me the 6 minus 8 times the inner product of v with itself. Right? Pull out 2, pull out 4. 4 times 2 is 8. So that'll be 3 times, well, this is just the definition of the length of u, but there's no square root, so I have to square it. It's length squared. minus 2 times, right, it's 4 minus 6, just give me the minus 2 for uv. And then minus 8 times the length of v squared.